Professor Thea explains.
What if I told you that the air you breathe, the screen you're looking at, and even you are all made of the same ancient ingredients that have existed since the beginning of time? Hey everyone, I'm Professor Thea, and for today's series, we will explore the fascinating world of science in a way that is fun, exciting, and easy to understand. Today, we're diving deep into a mystery that has puzzled humans for thousands of years. What is everything made of? Imagine a time when people believed everything was made of just four elements: earth, water, fire, and air. Now, fast forward today, where we've uncovered the tiniest building blocks of the universe, atoms. But how do we go from ancient gases to modern atomic theory? From the earliest ideas about what makes up the world to groundbreaking modern discoveries, we'll trace the journey of these tiny building blocks that shape everything around us. In this video, we'll explore how humanity's understandings of matter and atoms has evolved, from ancient speculation to cutting-edge science. Each era, from ancient philosophies, early modern chemistry, atomic theory, revolution discovery of subatomic particles, and modern atomic theory that brought breakthroughs that reshape our perception of reality, leading us to the deep, intricate knowledge we have today. But why does this history matters? Get ready and buckle up. It's going to be a mind-blowing ride. Today, we're traveling through time from ancient philosophy to cutting-edge science, Greek philosophers, to the labs of modern scientists to uncover the epic history of matter and atoms. Atoms are extremely small with diameters about many billionths of an inch, which make them impossible to be seen with the human naked eye. So, John Dalton worked with compounds, and he noticed that anytime compounds were made and they were actually made in the same exact ratio. Now, before microscopes, telescopes, or even the ideal scientific experiments, there were the philosophers, great thinkers who dared to ask, what is the universe made of? Where did everything came from? And how do we even begin to understand reality? For today, and first on my list, we're diving into the world of ancient philosophy, where the earliest ideas of science were born. Get ready to meet the brilliant minds who laid the foundation for everything we know today. Our journey begins around 600 BC in ancient Greece, where philosophers didn't have labs or technology, just their minds and curiosity. One of the first big ideas about matter came from Empedocles, who believed everything was made of four elements: earth, water, air, and fire. These ideas stuck around for centuries. But Aristotle had a clear idea. He believed that while the four elements explained everything on earth, there had to be something different in the heavens. He proposed the fifth element called ether. It means pure fresh air or clear sky in Homeric Greek. This mysterious substance filled the universe beyond Earth, making up the stars, planets, and celestial spheres. Unlike the four earthly elements, ether was eternal, unchanging, and perfect. Now let's rewind to around 400 BC in ancient Greece. Back then, people believed that everything was made of just four elements, but one thinker, Democritus, had a crazy idea. He said, what if we keep cutting something into smaller pieces? Eventually, you reach something so tiny that it can't split anymore. Democritus hypothesized that all matter was made out of indivisible particles that he called atoms. Democritus had this theory that all matter was made out of indivisible particles, and the problem with Aristotle and Democritus is they didn't have any scientific data. There were no data to back up their theories. adhering to an experiments or any test, they just assumed that this was the way that the world worked based off on their philosophy and their view. Now, many people thought that Democritus was crazy and they didn't understand how matter could be made up of tiny indivisible particles that we can't even see. This set up this set us back in the atomic theory by about 2,000 years, which is just crazy to think about if we had believed Democritus in the first place. Maybe we would have made some advancements in the atomic theory in year 1799. Joseph Paos proposed the law of definite proportion, and John Dalton formulated the atomic theory and proposed the law of multiple proportions. In the same year, Dmitri Mendeleev arranged the known elements in the periodic tables based on their atomic mass, and Anton Becquerel and Marie Curie observed that radioactivity causes some atoms to break down spontaneously. The one who discovered X-ray is Wilhelm Röntgen in the year 1895, while Henry Green Jeffreys Moseley used X-ray spectra to study atomic structure, and Robert Millikan found out that the charge of an electron is equal to negative 1.6022 times 10 minus 19 coulombs. This was until the early 18th, so almost 2,000 years later, another scientist came on the scene and his name was John Dalton. He made an atomic theory based off the evidence, so this was not just a theory that he pieced together through philosophy. This was actually based on scientific evidence, and there were a few things in his theory that are important to note. So, John Dalton worked with compounds and he noticed that anytime compounds were made, they were actually made in the same exact ratio. Every time, so for example, water is always H2O. It's never H30 or H2O2, or it's always H2O. There's always the same formula for a given compound. So Dalton's theory began by saying that everything was made out of atoms, which is what Democritus actually said back in 400 BC. He also hypothesized the atoms that couldn't be created and they couldn't be destroyed. He also thought that all atoms of a given element were completely identical. So for example, all carbon atoms would weigh the exact same and have the exact same properties. Every single time, he also thought that the atoms for different elements were completely different. For example, an atom of gold will be completely different than an atom of silver. So atoms of different elements were not alike, and then the last part of his theory had to do with compounds, and he said that atoms could come together and form compounds, and they will always form in the same ratio. Not too long after Dalton came another important discovery, our atomic theory, and that came from J.J. Thomson, and this was in the 1890s to early 1900s. Thomson discovered the electrons. Modern atomic theory builds on centuries of discoveries, refining our understanding of the atom and its complex structure. The 20th century introduced quantum mechanics, wave-particle duality, and the probabilities nature of electrons. The 20th century introduced quantum mechanics, wave-particles duality, and the probabilistic nature of electron behavior. Early 1900s, refining the nuclear model. In 1913, Niels Bohr's atomic model proposed that electrons orbit the nucleus in fixed energy levels. It explained that atomic spectra and electron transitions set the stage for quantum mechanics. In 1920s to 1930s, the rise of quantum mechanics. In 1924, Louis de Broglie introduced wave-particles duality, suggesting electrons act as both particles and waves. In 1927, Werner Heisenberg's uncertainty principle states that it's impossible to precisely determine both the position and momentum of an electron. In 1926, Erwin Schrödinger develops the quantum mechanics model, replacing fixed orbits with electron cloud regions where electrons are likely to be found. In 1932, the discovery of the neutrons, James Chadwick, he confirmed that the nucleus contains neutrons, solving the mystery of atomic mass differences. It led to deeper research into nuclear reactions and fission. In the mid-late 20th century, the Standard Model in 1940s to 1960s, scientists discovered quarks, proving that protons and neutrons are made of even smaller particles. In 1960s to present, the Standard Model of particle physics emerged explaining the fundamental forces and particles that make up the universe. The impact of modern atomic theory or the nuclear energy and weapons in Einstein and fission, the quantum mechanics in technology, the transistors, lasers, computers, and the medical advancements or MRI radiation therapy. Scientists like Bohr, Heisenberg, and Schrödinger helped uncover the hidden structure of matter, leading to incredible breakthroughs in technology, medicine, and even in our understanding of the universe itself. For nearly a century, this theory dominated chemistry until it was disproven by Antoine Lavoisier in the 1700s. 1703, George and Stahl developed phlogiston theory, claiming that all flammable materials contain a mysterious fire element called phlogiston. 1754, Joseph Bloch discovers carbon dioxide, calling it fixed air. 1772, Carl Wilhelm Scheele and Joseph Priestley independently discovered oxygen, though they didn't fully understand its roles, but early chemistry wasn't perfect. In the late 1600s, scientists believed in phlogiston theory, which claimed that all flammable substances contained a special fire element called phlogiston that was released during burning. The late 1700s chemistry had officially separated from alchemy. With the discovery of oxygen, the rejection of phlogiston, and the rise of scientific experiment, chemistry became a true science. From the fall of alchemy to the discovery of oxygen, early modern chemistry transformed the way we understand matter. In 1703, Georg Ernst Stahl develops phlogiston theory, claiming that all flammable materials contain a mysterious fire element called phlogiston. In 1754, Joseph Bloch discovers carbon dioxide, calling it fixed air. In 1754, Joseph Bloch discovers carbon dioxide, calling it fixed air. 1772, Carl Wilhelm Scheele and Joseph Priestley independently discovered oxygen, though they didn't fully understand its role. But early chemistry wasn't perfect. In the late 1600s, scientists believed in phlogiston theory, which claimed that all flammable substances contain a special fire element called phlogiston that was released during burning. For nearly a century, this theory dominated chemistry until it was disproven by Antoine Lavoisier. He introduced the idea that matter is made up of tiny corpuscles, an early version of atomic theory. Boyle also gave us Boyle's law, which explains how gases behave under pressure. This was a huge step toward modern chemistry. Phlogiston theory, a long-term chemistry. And so let's move on to the next topic. It's all about early modern chemistry. First on my list is the fall of alchemy and the rise of chemistry. In 1605, Francis Bacon promotes the scientific method, emphasizing observation and experimentation over mystical beliefs. By the 1600s, scientists started questioning alchemists' mystical ideas. One of the key figures was Robert Boyle. James Chadwick in 1932 finally discovered the neutron, and the neutron was the last to be discovered because it doesn't have an electric charge and it's not positive, it's not negative, so it was the more challenging subatomic particle to find for sure. A few years after Thomson's experiment, Rutherford came onto the scene in the early 1900s. Around 1907, Rutherford actually discovered protons in the nucleus. What Rutherford did was, as he shot positively charged particles at gold atoms, the atom looked like Thomson's model. Those positively charged particles should just pass right on. Overall, positively charged particles should just flow right through that matter, but that is not what happened. When Rutherford shot the gold atoms with positively charged particles, some of them hit the gold and bounced off in the opposite direction, which means that they had to hit something that was very densely positively charged, and most of the particles, though, went straight through the gold, which made Rutherford think that maybe the atom isn't just full of positively charged matter, but also an atom that is actually and mostly full of an empty space. So that must means that there's a dense positively charged center in the atom, which is called the nucleus. And the nucleus is filled with positively charged particles called protons. Next person who worked a lot with electrons was a Danish scientist named Niels Henrik David Bohr. That he made his theory around 1913. This model is known as the solar system model because it kind of looks like the solar system. What Bohr thought is that the electrons were moving in orbits around the nucleus. So here's our electrons moving in orbits around the nucleus, and he didn't think that electrons could jump between the orbits. Where he got this idea was from an atomic emission spectrum of hydrogen. Bohr was always correct, he was on the right track. But one problem with his theory was that his model actually only worked for hydrogen. It didn't work for any other elements on the periodic table. The next guy, and his name was Erwin Rudolf Joseph Alexander Schrödinger, was an Austrian-Irish theoretical physicist who developed fundamental results in quantum theory. In particular, he is recognized for postulating the Schrödinger equation. Schrödinger coined the term quantum entanglement in 1935. Schrödinger put his theory together in around 1926. Schrödinger put together the cloud model, and he agreed with Bohr that electrons have quantized energy, which means that again they have a specific amount of energy and they're in specific places around the nucleus. Schrödinger put this cloud model together and he looked at where electrons have been in the past and showed that there's a high probability that they're going to be in a certain location at any time and a given time. So the cloud model where you see is a high density of dots. That is where, and there's a high probability of finding an electron at any given moment. And the last person we need to briefly talk about was Chadwick. Not too long after Dalton, another important discovery was made, and it was an English physicist who received the Nobel Prize in Physics in 1906 for discovery of the electron, the first subatomic particle to be found. J.J. Thomson, or Joseph John Thomson, discovered the electron, and he discovered this by using something called a cathode ray tube. And in his tube, he had a stream of particles moving through his tube, and he held positively and negatively. charged plates up against his tubes, and what he found was that the negative plate deflected this stream of particles, so he knew that these particles must have a negative charge, and he called them as electrons. It is made up of positive matter sprinkled with some negative electrons mixed in, so his theory is called the chocolate chip cookie model, or known as the plum pudding model. From the ancient philosophers debating the nature of matter to the discovery of subatomic particles and the quantum mechanics of today, our journey through atomic theory has been nothing short of extraordinary. Each era, from Democritus' invisible atoms to burst energy levels, has brought us closer to unlocking the true nature of the universe. But science is never finished. With quantum computing, particle physics, and even the mysteries of dark matter, the next big discovery could change everything we know once again. Stay tuned for another lessons and topics.
Answer Thea explains.